All right, young people, this is Mr. Williams. I hope you are having a good evening. This is the evening of October the 7th, 2019. And it's about 6:30 p.m. Pacific Standard Time. So I'm going to try to make this video quick as I can, because I just got out of a bunch of meetings after working all day, and then I went to meetings, and now I came back to school just to make this video for you because I promised you I would. So I'm tired, but I am going to try to solve those last couple problems for you that I promised you that I would. So let me see where I was. We did. What is it? Oh, I think we were on 29, I believe. Yeah, I think we went 29 to 31. So let's pick up there. Let's see if I can. There. I wanted to zoom in and get you a decent look at the question. So we're in the night book. 29. A car traveling at speed v takes distance d to stop after the brakes are applied. What is the stopping distance if the car is initially traveling at speed 2v? Assume that the acceleration due to the braking is the same in both cases. So we have two cases. We have case 1 and case 2. So I'm just going to, let's see if I can arrange myself here so that I can work to try to solve this. All right. This is number 29. And let's draw a picture for case 1. All right. In case 1, you have a car. Now, I got to apologize in advance. I cannot draw. You already knew that. I told you that many times this year, but you're about to see it in action. Every car I draw looks like a sombrero, and I don't know what to do about that. That's just the way it is. So here's my car. Yeah, I know. I know exactly how terrible it is. So there's my car initially. It's got an initial velocity, v initial. And we'll call that initial velocity v. So it's got an initial velocity. But see, they didn't give us any numbers. So I'm going to use this letter v to stand in for my initial velocity. What is my initial velocity? It's 2v. The reason is because in my second case, I'm going to have a car going. Same car. Oh, well, it doesn't look the same. So there's my car, and it's going faster. Yeah, there's longer air contrails going out behind it. So v initial here is equal to 2v. Well, you see, it's going to be confusing already. I have a v initial and another v initial. So let's label them 1 and 2. This will be v initial 1 and v initial 2. Hold on just 1 second. I have to pause this. You mean to come back? So you guys just hold on. All right, kids. Sorry about that. The custodian was coming in to try to clean the room, and I had to talk to him for a minute. So hopefully you can all hear me again. Yeah, it looks like the computer has it going again. Where was I? Oh, yes. This is v initial 1, v initial 2. So this car goes, and in this case, the car goes till it stops, and it stops here. And v final for 1 is 0. And the acceleration for 1 is a, and the acceleration for 2 is also a, because it says in the problem that you have the same acceleration for both. And it says in the problem that you're stopping. So then the final It's got to be the same for both. So V final for 2 is equal to 0. All right, we've got 5 kinematic variables. T, I don't know what T is. It didn't tell me. That's T1, I don't know. T2, I don't know. And then, so this is D here. X1 is equal to D. What is X2? I don't know what X2 is. It says, what is the stopping distance if the car is initially traveling? So this is what I'm looking for. I'm going to circle it. I don't know. That's what I want to know. So if I were to go down my checklist, I don't know time, but I don't care about time. I know acceleration, I know final velocity, and I know initial velocity. So let me just write down my kinematic variables. X, T, VF, VI, and A. I know acceleration, I know VI, I know VF, I don't know T, and I don't know X, but I want to know X. So I need to know this, and I've got these 3. My kinematic equations are and all right, so I've got VF, VI, and A, and I need X. Well, there's no X here, so that's of no use to me. I've got X. Oh, but I don't know T, so that's of no use to me. Well, that makes life nice and easy. That is my baby. If I were to rearrange this, which I can do in my head by dividing both sides by 2a, then I'd get X is equal to VF squared minus VI squared over 2a. That's sweet. All right, so now I have a relationship for X. What do I do now, Mr. Williams? The sky is falling. Yes, I know, teenager. The sky is falling. It always is. So, not to despair. I'm going to give you a little hint. Let's look back at the problem. We are making a comparison here. Zoom in. We're making a comparison between 2 situations. We got a car traveling at V. We got another car traveling at 2V. Folks, anytime you see a comparison being made, I would like you to cast your mind back to middle school when you first learned about proportions, or elementary school, or whenever that was, and you learned about proportions that are of the order of A is compared to B as C is compared to D. And you learned like butterfly method and all kind of stuff, the butterfly method where you cross multiply and all this kind of stuff. This is a proportion. You got to remember the rules for that. You use this kind of stuff anytime you're making a comparison between 2 situations. We are comparing these 2 situations. So here's what I'm going to do. I'm going to say the distance in the first situation needs to be compared to the distance in the second situation as, see, the equality now can be referred to as as instead of is. I don't know if your teachers ever told you that in math class. The first quantity is compared to the second quantity as this third quantity is compared to the fourth quantity. What are these 2 things? Well, I have an equality over here. X is the same thing as VF squared minus VI squared over 2ax. So this must be the same as VF1 squared minus VI 1 squared over 2a. Now, I'm not going to say a1 because remember, well, I guess I will. I'll say a1 and then I'll change it in the next line. But remember, a is the same in both of them. So I could just say a, but I'm going to hold on and try not to be too complicated. So down here, it's VF2 squared minus VI2 squared over 2A2. Now we need to plug in here what we got up here. So let's take a look. Let's see if we can zoom out just a little bit more. No, I'm not going to be able to zoom out far enough, I don't think. So x1 is to x2 as, well, the finals for both cases are 0, so I'm going to cross them out. Yeah. And the 2's are the same in both cases, so I'm going to cross them out. And the A is the same in the top and the bottom because A2 and A1 are both A. The problem statement said you have the same acceleration both. So I'm going to cross the A's out. And all I've got is negative VI1 squared over negative VI2 squared. Okay, negatives are in the top and bottom multiplied by these two. So I'm going to cancel the negatives out. This makes my life so much easier. This becomes VI1 squared over VI2. Look at that, man. We went from crazy complicated down to really cool. Let's see what we have for VI1. Whatever we got has got to be squared. So VI1 is V. So we're going to get V squared up here. V is in parentheses because that's the thing getting squared. V is getting squared because VI1 is V. Now look here. VI2 is 2V. So 2V goes in the parentheses. 2V has got to get squared. Where the parentheses is super duper important because it tells you what you can square and what you can't. So this is going to be V squared over, now it's not 2V squared. The 2 gets squared too because you're multiplying 2V times 2V, so it's going to be 4V squared. Now I have a V squared in the top and bottom, so they're going to cancel out, and I'm going to be left at 1 over 4. So x1 is compared to x2 exactly the same way that 1 is compared to 4. The way I said that is super duper important. It's so important I'm going to write it out. x1 is compared to x2 the same as 1 is this should be compared to 4. Another way to do that is when I was in 7th grade, I had like this little old lady, and she was really mean. She taught me math, and she taught me the butterfly method. I didn't like her. She was terribly mean. But she taught me this thing called the butterfly method where you cross multiply and set them equal to each other. So this becomes, and your math teachers probably taught you something like this. This becomes 4x1 is equal to x2. So that means, let's look back at our picture, that I would have to go this distance here, x2, just put this up here, x2 is 4 times the distance of x1. So this x2 distance means you'd have to take x1 and multiply it by 4 to figure out x2. So the question asked us here, what is the stopping distance if the car is initially traveling at 2v? Well, if the car is going at 2v, then the stopping distance is 4d. It's 4 times the initial distance. Because if the initial distance was d, And this is 4 times that is 40. Let's move on to number 30. Gosh, I hope this one goes faster. I want to go home and have some dinner. Okay. Number 30. Light rail passenger trains that provide transportation within and between cities speed up and slow down with a nearly constant and quite modest acceleration. Yeah, because otherwise people would be complaining. A train travels through a congested part of town at 5 meters per second. All right, I feel like I need to draw a picture. Let's see, a train. Doesn't have like a thing up here. Yeah, and it does like this or something. Yeah. Okay, that's a train. And that's a track. So, your train is going V initial this way. I need that room right there. V initial. Oh, I'm sorry. I forgot that I zoomed out so you can see the book. I really do not like this ladybug. It is so annoying. I like my old one, but they said it was too old to use anymore and it quit working. But now I've got this stupid thing. Okay, so the initial is 5.0 meters per second. Once free of this area, it speeds up to 12 meters per second in 8 seconds. Oh, Lord. Okay, so whatever. Here's the back of the train. I'm not drawing the whole thing because I've run out of paper. So here's the back of the train, and VF is going to be equal to 12 meters per second. 12 meters per second. All right. And the time it takes is 8.0 seconds. At the edge of town, the driver again accelerates with the same acceleration. Okay, this is going to be a 3-part problem. This is annoying. So this is part 1. And then part 2. The driver accelerates with the same acceleration for another 16 seconds. So here we've got our train. V initial, well, if I got up to 12 meters per second here, got up to 12 meters per second here, then my initial here must be to the 12 meters per second that it got up to. And then it's going to, whatever my acceleration here is, that's the same acceleration I got here. And the time is going to be 16 seconds. And we need to know VF. God, I wish I could draw. Okay, so VF is unknown. And the question is, what is the final speed? So I got to find this. Here's my game plan. I can see it already. I need to figure out the acceleration in this bit. Once I know that acceleration, then I can use that acceleration here to figure out the final velocity. That's my whole game plan. Ugh, what an annoying thing. So let's do it. I really want to get done. I've got VF, VIT, VF, VIT, A, and X. I don't know X, but I also don't want to know X. I want to know A, and I have T and VI and VI. So A is equal to VF minus VI over T. That's good enough. I'm not going any further. That first, this equation works. I'm not writing the other three down because I see that works, and that's going to do it for me. VF is 12 meters per second, and VI is 5 meters per second, and the time is 8 seconds. So where I put that calculator? Oh Lord, it's 12 minus 5 is 7. 7 over 8. 0.875. 0.875 meters per second squared. So that's my acceleration. So I'm going to go back up to my picture and draw that in. Equals 0.875 meters per second squared. 875 meters per second squared. Okay. Now I'm going to need to get another sheet of paper here. Give me just 1 second. The next bit here, what have I got? I've got VI. I don't have VF, and that's what I want. I have A. I have T. I do not have X, but I don't care about X. So my equations are and oh Lord, what did I write that for? That's not a delta T, that's delta V. I must be tired. Okay, what am I looking for? VF. I could get a VF here. I've got A, I got T. Yeah, this would work, wouldn't it? Yeah. I've got A, I got T, yeah, this works. Forget about the rest of them. I'm using this one. So A is equal to VF minus VI over TF minus TI. TI is going to be 0, so that's gone. Multiply both sides, I'm going to get ATF is equal to VF minus VI, and I want to know VF, so ATF plus VI is equal to VF. Great. VF must be equal to, my A was 0.875 meters per second squared times the time, what did they say it was? 16 seconds. 16 seconds plus, oops, not times, plus the initial. Okay, the initial would be 12. So I already got my 0.875 from before. Multiply it by 16 times 16. That's 14 plus 12. That's going to be 26 meters per second. Let's see if I got the right answer, please, Lord. Yes, I did. That's the right answer out of the book. Good. Sounds good to me. Just one more of these things, and I can finally go home. I mean, it's fun doing math, and I love physics, but I am tired. Let's do number 31. A small propeller airplane. Oh, gosh. I have to draw an airplane. Oh, no, that's 32. Okay, 31. Let's zoom in here. A cross-country skier is skiing along at a zippy 8 meters per second. She stops pushing and simply glides along, slowing to a reduced speed of 6 meters per second after gliding for 5 meters. Okay, so she's going at 8 meters per second. Then she slows to 6 meters per second over 5 meters. What's the magnitude of her acceleration as she slows? Oh, this isn't too bad. I don't think it's too bad. Well, we'll find out if it is. First thing where I'm going to do is draw a picture. And, of course, you can imagine how good that's going to be. Just about as good as it always is when I draw pictures. So here's my handy-dandy person. Okay. And this person is in skis. That looks like a ski. Yeah, that looks like a ski. I don't think that's how you're supposed to ski, but... And don't they have, like, ski poles or something? I have never skied. My family didn't have money for that. If we had money, we weren't skiing, I tell you that. Okay, so there you go. I think this is probably not how people ski, so I'm just going to, like, make him look dissatisfied with life. So he is going, let's say, I guess he's going this way. He'd probably be falling down, actually, but his initial velocity is 8 meters per second. Zippy 8. Yes, that is quite zippy. Oh, and it's a girl. It says she. So let's give her some hair. And there we go. She stops pushing and glides along. She slows. So she's going to slow down. So she's going to slow down. Air's coming out behind her. And then here she is later. Oh, God, I got to redraw this. Yeah, that's probably what I would look like if I were skiing. So her final velocity now is 6 meters per second. Oh, Lord. I tell you what, if there was the worst artist in America category, I think I would win. That is just terrifying. It looks like modern art or something. So 8 meters per second. Well, I guess it is. It's modern. I just made it, so it's modern. So this young woman goes 5 meters as she slows down. And we're supposed to find we are not supposed to find her acceleration. Oh, folks, that's tricky. Look at that. It does not say find her acceleration. It says what is the magnitude. Magnitude, remember, in physics means size or absolute value. So I'm going to write that down. Magnitude means, I can't spell, size or absolute value. Oh, my Lord. Ugh. The thing was not in the screen. I'm sorry, kids. I was just writing this down. Magnitude means size or absolute value, but this ladybug, if I could show you how annoying this thing is. Whatever. That's my problem, not yours. So we have to find the size or absolute value. Let's write down our 5 kinematic variables. They are VF, VI, X, T, and A. I do not know A, and actually I want to know the absolute value of A, so I'm going to circle that. I do not know time, but I also don't want to know time. I know the other 3. So my kinematic equations are that works. Oh, but I guess I'll just write the other ones down so you can see my thinking process. And okay, I don't know time. I don't want to know time. That's out. I don't know time. I don't want to know time. This has got time everywhere. That's out. Boom. That's how I picked that one. So let's go for it. I want to solve for A. I'm going to do this algebra in my head. Divide both sides by 2x, and you get a is equal to vf squared minus vi squared over 2x. So VF, looking up at my marvelous picture, VF is going to be 6. I'm like starting to do it in my head. I'm so tired. It's not 36 yet. We have to write it down for the teenagers. So that's going to be 6 meters per second squared minus, and then the initial is going to be 8 meters per second, and then you squared, and then 2, and then the distance is 5, and then you can do it in your head or plug it into your calculator. So just so I don't look foolish, let's do it in the calculator in case I mess up. So that's going to be 36 minus 8 times 8. God, what is 8 times 8? 64? See, this is why I'm going to look foolish. I sure hope it's 64. Yeah. Guys, yes, it's 64. I'm doubting myself at this point in my life. I should not do that. So 36 minus 64 divided by 2 times 5, negative 2.8. Let's see if I got the right answer. Let me look in the back of the book here. Oh, no, that's not the right answer. It's almost the right answer. It's not, because I didn't answer the question. The question was not find the acceleration. The question was find the magnitude of the acceleration. This is the acceleration. So I shouldn't have put a box around it yet. I'm not done. This is why I should be home eating pizza, watching Netflix. But no, I'm here doing physics. Okay. This is A. So the absolute value, oh, there went my pencil. The absolute value of A is equal to 2.8 meters per second squared. That's that. Folks, it's been real. It's been fun, but it ain't been real fun. So y'all have a good evening. I will see you tomorrow.